So this has to do with the ARC Center of Excellence in Future Low Energy Electronics Technologies, which was just funded, which I am directing. This Center of Excellence is directed at a particular challenge, and that challenge is that we have an insatiable desire for computing. So the demand for computations is growing at something like 70% every year, the number of computational operations that's done on the planet. That has been largely offset due to gains in efficiency due to Moore's law. Not completely, so the energy that's used in computation is growing at maybe 7 or 8% a year, but much lower than the 70%. But we all know that Moore's law is coming to an end, and in fact, transistors are really ceasing in terms of gaining efficiency in energy per computation. And so the semiconductor industry realizes that there's a need to invent and reduce to practice a new information processing technology eventually to replace CMOS. So this comes from the semiconductor roadmap. And so the whole goal of Fleet Center is to come up with a new switch that has vastly lower energy per computation. The approaches are rather specific. We want to look at new mechanisms for electronic conduction without dissipation at room temperature. So those might be topological edge modes that I talked about in this talk, excitonic condensates, or non-equilibrium topological or superfluid states. And then the idea is to make sensitive switches based on either quantum phase transition, such as trivial to topological, or collective electron phenomena, such as a superfluid condensate. So I'll talk about just these two topological ones. So one of the themes of Fleet then is to come up with a topological transistor, and so that would be a 3-terminal device controlled by where the current from source to drain is controlled by a gate. And what that gate does is it can turn a channel material from conventional to topological. And so when this is a conventional insulator, it doesn't conduct. When it's topological, it would have these edge modes that carry current in one direction without dissipation. So there are a number of people in this team. There are 6 investigators at Monash. I think I can point them out. So there's myself, there's Mira, Chris, Nikhil, I found 4, Augustine, and Xiao Lang, who's here somewhere, right? So he's in the middle. Okay, so, and we have 3 different themes. So in addition to the topological dissipationless systems, we're looking at, again, excitonic condensates and dynamically controlled non-equilibrium systems. So I'll talk just a little bit about this because this is something that I'm doing research on, just to tell you where this is going. We talked about the difference between a conventional insulator and a topological insulator. The topological insulator comes about because of an inversion of the valence and conduction band. So there's typically an axis that one can run along. It could be concentration or strain or what have you, that will transform a regular insulator to a topological insulator. And what has to happen is the gap has to close in between. And so that can't be done because they're topologically distinct. It can't be done without somehow changing the topology, and that has to happen by going through a metallic phase. And so we know there's always a metallic phase in the middle. This is generically what's called a topological Dirac semimetal. So topological Dirac semimetals are at this quantum critical point between regular and topological insulators. And examples of that, again, are graphene, which has this touching of bands. And we know that we saw earlier that graphene can be turned into a topological insulator, for example, by adding spin-orbit coupling. So it turns out actually these things exist in 3 dimensions, and so this is something that was realized only fairly recently, that there are 3-dimensional topological Dirac semimetals. Sodium-3 bismuth is one of these. And so this has this Dirac cone, but in all 3 momentum directions instead of just 2 as in graphene. And there are other examples of these 3D topological Dirac semimetals. Cadmium-3 arsenic-2 is clearly one. Zirconium telluride may be one, and there may be others. So that's rather nice, because if we have this topological Dirac semimetal, we can perturb it, push it one direction or another, and create either a topological insulator, which has dissipationless edge modes, or a conventional insulator, which is insulating. And there are examples of this, at least in theory. So for instance, if I take sodium-3 bismuth and I make it very thin, I can turn it into a conventional insulator just by confinement. And then if I apply an electric field, I can change that conventional insulator to topological, and it'll go through this semimetal phase in between. So this is the energy gap as a function of electric field, and it starts conventional, it goes down to 0, and then it becomes topological. And in this state, it would have this conducting edge mode that could be dissipationless. So this is exactly what we want. It's a topological transistor. It goes from insulator to something that has this conducting edge mode. And so this is a material that we're working on in the lab. So if you go over to New Horizons and look in the window, you'll see this machine here, which Mark, my postdoc who's here, calls the echidna. Because it has lots of spiny projections coming off of it. So this is a great machine. It allows us to grow materials like this sodium-3 bismuth, and then transfer them into a scanning tunneling microscope at low temperature, where we can not only look at all the atoms in the material, but we can also do electrical experiments on that material. So these materials are actually grown on pre-existing electrodes on insulating substrates that are all wired up to do electrical measurements, and we can go in with the STM and image. These are sort of atomically flat terraces of this material, and these are the atoms with an STM. And I'll just show you a couple of results that have recently come out. So we've been able to make this material and measure its mobility for different samples with different carrier density. We get really nice mobility. This is about where people started with graphene at 6,000 centimeters squared per volt second, and pretty low carrier density. This is a really fantastic sample that Mark and James have been able to grow that has really large terraces, and now they're mapping out the local Dirac point in this material with scanning tunneling spectroscopy. You can see this minimum, which corresponds to the Dirac point, and map out its spatial variation. And these are sort of maps of the spatial variation of the Dirac point. And the really nice thing is that we can get really close to the Dirac point in energy. So the Dirac point, it only varies by a few millivolts, 5 millivolts in space. And that's comparable actually to the very best graphene samples. So it tells you sort of how close you can really realize this Dirac-like band structure, how close you can get to the point of that cone. And it's comparable to the very best graphene samples. So that looks really good as well. So what we're trying to do is make these very thin films to see this transition to a conventional insulator, and then apply an electric field and see a transition to a topological insulator.